Given an equation, we're asked to show that there's no stationary point. So first up, let's find dy by dx, the derivative. Differentiate is going to give 3x squared minus 6x plus 4 using our rule of powers that we have for differentiating x to the n. And I could try and set this equal to 0 and show that there's no roots. That is actually one way. Or because I want to show there's no stationary points, that's going to be when it's going to be always greater than 0, basically, which is the same. You know, when you have no roots, you're either like this or like this. We can see it's a positive quadratic. So I'm going to complete the square. 3, it seems to be like set up quite well for completing the square as well because there's no fractions involved. So that's the first step. And then complete the square on x squared minus 2x, we get x minus 1 all squared minus 1. I'm not going to go into detail on that. Do practice it if you're not confident with it. And I've got other videos, AS papers and similar, where I go into much more detail on completing the square. Expanding the bracket then gives, I'm going to get a minus 3 and a plus 4, so it's going to be plus 1. This is greater than 0 for all x. So there are no stationary points. 2, I did mention it. Let's look at the discriminant. So b squared minus 4ac. And this is for the derivative, not the cubic. The cubic doesn't have a discriminant. So b squared is going to be minus 6 squared, or 36, minus 4 times 3 times 4. That's 48. So I'm going to get minus 12, less than 0. No real roots. And this implies 3x squared minus 6x plus 4 cannot equal 0, and hence there's no stationary points. So that's another way to do it. Moving on, we're asked to show that the curve has exactly one point of inflection. So the point of inflection is when the second derivative changes sign. So it's when the gradient goes from increasing to decreasing or vice versa. We say concave and convex. Concave for the gradient decreasing and convex for the gradient increasing. Anyway, let's just focus on finding the second derivative. So we can take our first derivative and differentiate again. It's going to be 6x minus 6. Now in some questions, it's good to like seek when the second derivative is 0 and then just show that it changes sign when it's slightly above or below. It's actually quite a complex topic, the point of inflection, going beyond A level. So you can also get points of inflection where I feel like I mentioned this in every video I do on this, but you can have the second derivative changing sign without it ever becoming 0. Now that is not going to happen here because we've got a linear function. So in fact, I'm going to look at when it's concave. This is when 6x minus 6 is less than 0. So x is going to be less. I can add the 6 on, then divide by 6, let x is less than 1. And convex, when 6x minus 6 is greater than 0, so x is greater than 1. So clearly see that it's going to change sign at x equals 1. We could have set the second derivative equal to 0, but you still have to then check that technically that it changes sign. So this just feels easier because it's such a simple second derivative. Changes sign at x equals 1. So there is, what did it say? Did it say only 1? There's exactly 1